Everyone. We're going to solve this problem on preparing a diprotic buffer by adding either H or OH. And in this example, it looks like we're going to be adding OH. They want to know how many milliliters of this sodium hydroxide should be added. So OH is going to be a reactant in my neutralization reaction. And what are we adding that to? Well, it looks like we're adding it to potassium hydrogen phthalate. So I hope you're thinking what I'm thinking. If potassium is a +1, the counter ion, hydrogen phthalate, must be a -1, and this word hydrogen is a clue that you've got HA-. If it just said potassium phthalate, that would have been A-2. So we're going to add OH to HA-, and the final pH is going to be 5. Let's write that neutralization reaction. OH getting added to HA- to form water and the missing A-2. Now, notice that the desired pH is close to pKa2, isn't it? That means that the final buffer must contain HA- and A-2, so I'm glad that both of these species appear in our neutralization reaction. So let's go ahead with an ice table, and remember how I said that OH reacts with HA- to make the missing A-2. Well, if A-2 is missing, that would be 0 for the initial. How many moles of OH do we have initially? We don't know. That's what we're trying to find out. And I think the moles of HA we can figure out because we're given volume and concentration. I got 0.00137 with an insignificant 5 moles of HA initially. So now reactants go down, products go up. But what do we subtract? The X or the moles of HA-? Well, if you subtract the moles of HA-, you're not going to have a buffer. HA- will go to 0 and you won't have a buffer anymore. So subtract the moles of OH from the reactants, add it to the products, so that at equilibrium you don't have any more OH. You have 0.001375 minus X for HA, X for A-2, and now we're all set to use the Henderson-Hasselbalch equation. So the pH equals the pKa plus the log of A-2 over HA-. So all we have to do is solve for X. You've probably gotten pretty good at solving these logarithmic equations by now, but whatever you do, don't ignore this X. And that's because this reaction goes to completion. All neutralization reactions go to completion. In other words, X will not be small. So I'll go ahead and solve this equation. You may feel like you can fast forward through this part, which would be okay. Subtracting the pKa from both sides gives 0.40 with an insignificant 8, and I think that's a negative. And we're going to have to take the anti-log of both sides to get rid of this log. And if I have 2 digits in the mantissa of A, when I take the anti-log of this number, I'll need 2 sig figs. That's 0.39 with an insignificant 1. I'm going to multiply both terms by this denominator, both sides of the equation, I should say, by this denominator here. And then distribute this number across the 2 terms in this equation. And then adding 0.39x to both sides gives 1.391x equals 5.37 times 10 to the negative fourth. And then x dividing both sides by 1.39 gave 3.8 with an insignificant 7 times 10 to the negative fourth moles. And that's the moles of A minus 2 that we made. That's the moles of HA minus that reacted. And it is the moles of OH that we need to add. And if that's the moles of OH, that's the moles of sodium hydroxide. So they wanted to know how many milliliters of this solution. So we're going to have to convert those moles into volume using that concentration. For every 0.15 moles of sodium hydroxide, there's 1 liter of solution. And then the final step would be to convert those liters into milliliters. And when I did the arithmetic, I got 2.5 with an insignificant 8 milliliters. I hope you got the same answer, and I hope you try more of these examples on your own. Thanks for listening, and good luck.